Hello everyone. In this video, I will explain the topic which is noise in the FM receiver. That is, what is the impact of noise, a AWGN type of noise which is added with the transmitted FM signal. Okay, and when I demodulate it in the receiver, what is the impact of that noise on the recovered signal, that is the message signal. So let us understand this using this block diagram. So this is the model representation of you can say the receiver section. Okay, so in the channel usually I have a FM signal, transmitted signal which is transmitted with a certain bandwidth. A noise, additive wide Gaussian noise with a zero mean and a power spectral density of say n0 by 2, okay, is added with this transmitted signal. Now that combined signal, that is FM signal as well as the noise, is now input for my band pass filter. So band pass filter is designed to have a bandwidth of say BT, that is the transmission bandwidth. So that is, it is designed to allow only the FM signal which you have tuned in the receiver. Okay, if I say that your bandwidth is say around 200 kilohertz, that's what usually is assigned for the different FM stations like Radio Mirchi or Big FM and all those stations. So the transmission bandwidth of this band pass filter, or you can say it is the pass band of this band pass filter, is restricted to around 200 kilohertz, that is BT. Okay, so it is centered around FC with the overall bandwidth of plus or minus BT by 2. Okay, that is the bandwidth of this. So a noise passes through along with the signal, FM signal. Noise also passes through this band pass filter, and in the output of that, whatever the noise we get is restricted only within the bandwidth of BT. Okay, not infinite bandwidth, or what you say, because the additive wide Gaussian noise has a spectrum equal to n0 by 2 between minus infinity to plus infinity, the frequency domain, right? But here it is restricted only between minus BT by 2 to plus BT by 2, you can say, or maybe you can say overall bandwidth of BT. That is, let us take that noise as n of t in the front end of the limiter. Now, what is the use of this limiter? A limiter is used to limit or control the amplitude variation, whatever happens in the FM signal. Okay, so that signal, the output is given to the discriminator, where the signal is demodulated and will get the output as V of t. And in the absence of the noise, I expect this V of t simply to be equal to m of t with some certain scaling factor, no problem. But in the presence of noise, along with m of t, I will get certain noise component also. So what exactly we will get, I'll explain this in the next slides. Then it is passed through a low pass filter, and that low pass filter will allow only the message signal. Okay, so that's what the message signal is. Now you can say that the message signal is recovered by using this receiver, FM receiver, I can say. Now, so as I told earlier, in the band pass filter, the output of the band pass filter, the noise component, whatever it passes or allows the band pass filter, I'll take it as n of t, and this n of t is actually given by this particular equation. Okay, that is the in phase component I have. So I have an in phase component here, ni of t, a quadrature component nq of t is a band pass signal, right? But these two are the low pass versions, equivalent versions, in phase and quadrature, cos 2 pi fct and sin 2 pi fct. So I take this as n of t. Now, so what we have to do here is next, or in another way, I can represent the same n of t in the form of say envelope or a magnitude and the phase or angle term, that is psi of t. Okay, r of t cos 2 pi fct plus psi of t is the equivalent representation of the noise component, that is n of t in the output of the band pass filter. Okay, now what is that r of t is? Is nothing but it is the envelope. You can say r of t is the envelope of the signal, noise signal. Psi of t is nothing but it is the angle. Okay, now, so I can calculate this r of t as I told, it is nothing but it is a magnitude. So how do you calculate the magnitude? It is nothing but it is root of, that is root I have taken here to the power half, root of square of the in phase component ni of t, right, square of the nq of t. So that's what I have taken here. What about psi of t then? The psi of t is nothing but it is the tan inverse of nq of t by ni of t. Now I know how to calculate this r of t and psi of t is, right? Now, what is the incoming FM signal? This is about the noise. This is about the noise component. Now, what is the FM signal? FM signal is nothing but it is given by this particular equation. That is, it is AC cos 2 pi fct plus 2 pi kf integral of 0 to t m of t dt. Okay. So in this equation, let us say a second part. This part I will take it as phi of t. Okay. The phi of t is given by 2 pi kf integral of 0 to t m of t dt. Okay. And I replace it in the equation. So I'll get the equation as s of t is equal to AC cos 2 pi fct plus phi of t. So now I know what is the basis component is, sorry, the input signal is, that is the modulated signal, and the noise component, right? So now this noisy signal, whatever the signal you have in the output of the band pass filter, which I have taken it as x of t in my representation, the block diagram. So that x of t is given by what? It is the sum of s of t when n of t. Okay, this is the available signal in the output of the band pass filter along with the noise component. And if I substitute both the terms, I'll get the equation something like this. That is AC cos 2 pi fct plus phi of t plus the noise component is equal to R of t cos 2 pi fct plus psi of t. Now, this equation, the equation for x of t, can be represented in the form of the phasor diagram or phasor representation. Now just look at this equation. So this line is nothing but it is the 2 pi fct component, right? So for this 2 pi fct, there is an angular variation of phi of t, right? Isn't it? With the amplitude equal to AC. So I have to represent this AC with the angle variation of phi of t. So that's what I have represented over here. This line actually represents the magnitude of AC, okay, with forming an angle of phi of t with respect to cos 2 pi fct. Okay. Now for this particular signal, again another component is added, that is R of t. So what is this R of t is? Again this R of t, just look at this, R of t is shifted by, with respect to the 2 pi fct line, it is shifted by psi of t, right? So this same R of t, or you can say this is your R of t, okay, it actually forms the angle of, or this is the parallel line what I have shown here. With respect to 2 pi fct, it has formed the angle of psi of t, right? So this is the line and this is the line. Now what I will do is I'll take a resultant here. How to take resultant? Just extend this, okay, extend this here and join. Okay, so this is the signal x of t what I'll get. Now you have to notice few points here. Those points are, I know this is psi of t, this is phi of t, right? Now I'll take this angle as phi of theta of t. I take this angle as theta of t. Now what is this angle then? This angle is nothing but it is theta of t minus phi of t, right? So this angle is theta of t minus phi of t. So I have this triangle shape here, representation, the vector, okay, where again one more thing is I have assumed that AC is very much higher than the noise component. That is, the amplitude of the FM signal is very much higher than the noise component in this particular example. Now, so this actually forms another angle here, that is psi of t minus phi of t. Okay, you can verify that this is psi of t minus phi of t is nothing but this angle, right? So I can extend this as, I can take this as R of t cos of psi of t minus phi of t. Okay, this one, and this is nothing but it is the vertical line which is quadrature in phase. So I have this as R of t sine of psi of t minus phi of t. Now, so using this phasor diagram, let us write few equations. What is this equation is? So I'll get an equation for this, that is theta of t minus phi of t. So that means if I take this phi of t on the other side, I can write an equation for theta of t minus phi of t. So this is the angle what I am writing. Angle is represented as always tan inverse of something, right? This is tan inverse of this by this. Okay, so here I have AC plus R of t cos psi of t minus phi of t. That is in the denominator actually. I said this is the ratio of this to this, right? So this line is nothing but it is R of t sine of psi of t minus phi of t, that I have written in the numerator, and AC plus this component is nothing but in the denominator. Fine. Now we will make certain assumptions. Now what are those assumptions? Then let us apply those assumptions over here. The assumption is, let us consider that the CNR, that is the carrier to noise ratio, is very much higher than 1. That is AC is very much higher than R of t. So with this assumption only, I have drawn this phasor diagram, right? So in that case, I can say that AC is very much higher than the second part, that is the noise component, that is R of t. Correct? This is very much smaller. So in that case, I can neglect this R of t cos of psi of t minus phi of t. Okay. Now, so AC is very much higher. The numerator is smaller quantity because it is a noise component, right? So tan inverse of a smaller number. This ratio is always a smaller number because the denominator is very much higher than the numerator, right? So tan inverse of a small number x is nearly equal to x. So that means I can omit this tan inverse. I can neglect this, okay, and I can write an equation as something like this. So what I have written here, that is phi of t plus R of t sine psi of t minus phi of t divided by just AC. Okay, so I substituted phi of t also here. The phi of t is nothing but it is 2 pi kf integral of m of t dt, which I have taken earlier, right? Now, I have a discriminator. Okay, the output of this discriminator, that is a frequency demodulator, is always proportional to the differentiation of the theta of t. Now I know what is the equation for theta of t here, right? In the previous slide, yeah, this one is theta of t, correct? Now the differentiation of this theta of t is nothing but it is the output of the discriminator. So let us do one thing. Let us substitute those things. Okay, that is, you can say that the output of the discriminator, that is a demodulated signal, is nothing but it is differentiation of this theta of t with some scaling factor of 1 by 2 pi. Or we can say that one more thing what I can add over here is V of t is actually proportional to the instantaneous frequency, correct? So V of t, the output of the demodulator, is actually proportional to instantaneous frequency. So whatever that is, because in the modulator what we did is we changed the frequency of the carrier proportional to the instantaneous voltage of the basic signal. So it is opposite, right? Isn't it? So what is Fi of t? Well, Fi of t is nothing but it is 1 by 2 pi d by dt of theta of t. Okay. Now let me erase whatever I have done here. Okay. Now, so I substitute that theta of t from the previous equation. I substituted over here. Then I'll substitute phi of t. So phi of t is equal to this, right? Let us integrate. I mean, let us integrate or differentiate this particular term. Here we have a differentiation of the two sum terms. So separately I can write it, and differentiation of d by dt 2 pi kf integral of m of t plus d by dt of the second term, right? So the differentiation and integration cancels over here. So I get an equation something like this. Okay, that is, in this case, this 2 pi and this 2 pi cancels. I left with a kf and m of t. Because the integration differentiation cancels, I'll get a k of m of t from the first term. The second term is 1 by 2 pi into AC differentiation of r of t sine of psi of t minus phi of t. So in this equation again, let me make a small substitution. This is the quadrature part, right? This is the quadrature part because it's a sine psi of t minus phi of t. So what I'll do is I'll replace this entire term by nd of t. Okay, that is the noise in the discriminator output. That is nd of t. Now, what is nd of t? Nd of t is nothing but it is 1 by 2 pi AC. That is second part of this particular equation, right? So in that equation again, let me make a small. Yeah, this is just a description of whatever I have just now told. So let us make some additional substitutions for this, which I'll explain in the next slide. So what exactly I have given here is the discriminator output V of t consists of the original message signal. Just look at this. We have a message signal m of t with some constant of proportionality or a constant factor of kf along with the noise. So I can say that the V of t is nothing but it is the message signal m of t. We recovered a message signal, but there is a problem with this noise, right? The additive component of noise nd of t. This additive noise at the discriminator output is determined essentially by the quadrature component, right? Because nd of t is nothing but this particular part, which is a quadrature component of the narrowband noise m of t. Now, I'll take up that same equation once again, that is nd of t. So in this particular equation, let us replace this quadrature component by a single term, let us say that is nq of t. Fine. So this entire thing is replaced by nq of t. So we have a d by dt of nq of t because it's a quadrature component, correct? So it's a quadrature component as I told just now. So where nq of t is nothing but it is r of t sine of psi of t. So now, what does this means? This means that the additive white nd of t is appearing in the discriminator output is determined effectively by the quadrature component, that is nq of t. Now, let us calculate. So I have an equation right now, okay, for a b of t, that is demodulated signal. So using that particular equation, let us calculate what is the signal to noise ratio in the output of the discriminator. Okay. Now for that we have to calculate what is the signal power is, what is the noise power is, and take the ratio of both. I'll get a output SNR. Now what is the signal power? Okay. So my equation is this, as you are already have seen now. This is the equation. This is the message part. This is the noise part. Okay. So we have to calculate the signal power, then the noise power. The signal component is very simple. M of t can be replaced by a P, right? Where P is equal to the power of the message signal. Okay, M of t, which is given by AM square by 2, and the power is given by what? Kf square, okay, into P, because Kf is a simple constant. Kf square into P. So the signal power is Kf square into P. So now the task is to find the noise power. So it is a bit lengthy. Now I'll explain that in the next slide. Now, how to calculate the average noise power? Now, so we know that nd of t is nothing but 1 by 2 pi AC into d by dt of nq of t, right? So we have derived that equation. I take a Fourier transform for this particular equation on both the sides. Fine. Now, what is the meaning of this? So the Fourier transform of say d by dt of x of t, a particular signal x of t, is nothing but it is j 2 pi of x of f. So I have a nq of t here. So if I take a Fourier transform to the differentiation of nq of t, it is j 2 pi of nq of f. That's what I have to get. I will get. Okay. The same thing I have explained over here. So it's j 2 pi f multiplied by nq of f. Okay. Now, so we may obtain this, the noise process here, nd of t, by passing nq of t through a linear filter with a frequency response which is equal to this. Okay, just to get this equation. So this is the equation. Okay, so what I have done over here is 1 by 2 pi AC, and I have substituted the j 2 pi f. It is equivalent to saying that we can process this nd of t by passing the nq of t through a linear filter. That is this nq of t through I can get this nd of t by passing nq of t through a filter which has the response equal to 1 to j 2 pi f. That's it. Okay. So 1 by 2 pi AC into j 2 pi f. That's what I have taken from this equation. Okay. I'll get jf by AC. That is g of f. So g of f is the filter. Okay. To which I am passing nq of t to get nd of t. Okay. That is in the spectrum representation. You can say that the power spectral density, whatever I will get in the output of such filter, okay, the power spectral density S nd of f, okay, of the noise is related to the power spectral density of nq of f. So S nq of f is nothing but it is n naught by applying a frequency shifting at all, because it is centered around 0 now. Okay, minus bt by 2 plus bt by 2 with a overlapped value of n naught. That is the value. So if I pass this nq of f, S nq of f, the PSD, through a filter which is g of f, okay, and let us, in this case I have taken as h of f, in this derivation I have taken it as g of f. If I pass through, what is the equation I will get is the output of such filter, okay, the PSD, is given by this particular relation. I think I have in one of the video I have explained this relationship. The PSDs are related by this. Now, so S nd of f is, but it is the square magnitude of the filter response multiplied by the PSD in the input, right? So this is the input. I am passing through a filter with a response of this particular response. Okay, the output is nothing but this. This is what I will get as the output. Now, why we get such a response? You can verify that by substituting this. Okay, just substituting this g of f over here. What is SNQ of f? SNQ of f is nothing but it is n naught. That's what I will substitute that later. G of f whole square. If I take a square magnitude of this particular function, it is square magnitude is, so j will disappear. F square by AC square into SNQ of f. Okay. Now, if I substitute different frequencies, say f equal to 0, what is SND of f? If f is equal to 0 at this particular point, if f is equal to 0, SND of f is also equal to 0. If f is equal to some, say 1 hertz, 2 hertz, or whatever it is, if I go on increasing the frequency, okay, positive or negative, the SND of f actually increases square of the frequency, right? That's why you get a response something like this. It's not a linear variation, it's a square of the frequency. Fine. Now, in the next slide, I'll substitute that n naught. I have substituted over here because nq of f is n naught, f square by ac square within the bandwidth of minus to the plus bt by 2. So that means I just represented this particular representation by using the equation. That's it. So between minus bt by 2 to plus bt by 2, okay, I have a n naught multiplied by f square by ac square is the response of this SND of f. That is the PSD at the output of discriminator. Now, after passing through discriminator, the next block what I have in the my block diagram is a filter. That is a low pass filter. A low pass filter will have a bandwidth which is equal to the message bandwidth, that is minus W2 plus W, which is very much smaller compared to the transmission bandwidth, that is 200 kilohertz, right? This bandwidth is very small, maybe 10 kilohertz, maybe 20 kilohertz audio band, right? Isn't it? Roughly. So this bandwidth is very small. So that means when I pass this noise component through a low pass filter which has the response of, say, if I draw the response here, just one second, a low pass filter which has the response equal to this, filter response something like this maybe, okay, if I pass through this, I'll get the same spectrum but within a restricted between minus W2 plus W. So I will apply this concept in my next slide. Just look at this. So this is the SND of F, input to the low pass filter. Then after passing through the low pass filter, what I will get is this, the same spectrum, but the bandwidth is limited to minus W2 plus W, or the magnitude of the frequency is W hertz, because W is very much smaller than Bt by 2, right? So this means the out of the band components of the noise will be rejected. That means above plus W and minus W, okay, the noise component will be rejected now. We have to calculate what is the average output power is. Okay, I know what is the PSD of the noise. So we derive the PSD of the noise, which is given by this particular formula. That is N0 into F square by AC square. This is the PSD. Okay, what is the output power then? Power of the noise is nothing but it is the area under the curve of SNO of F. That is the output of the filter, right? Now, so how to calculate area under the curve? It is integral of minus W2 plus W is a low pass filter, F square multiplied by N0 by AC square, because it is a constant, so I have taken outside. Okay, then what is the integration of F square? F cube by 3, right? Then substitute the limits, I'll get this particular equation, that is 2 times N0 W cube divided by 3 AC square. Now, so we obtain this particular equation, just a small error in the presentation. So what is the average power of the signal? It is nothing but it is kf square, okay, into p, okay, now divided by 2n0 w cube divided by 3ac square. So this is the signal power. We have derived it earlier. Now I know the noise power also, which is given by 2n0 w cube divided by 3ac square. Take the ratio of both, I'll get the formula something like this. Okay, so this is the signal to noise ratio in the output of the discriminator. Now we have to calculate the signal to noise ratio in the channel. Okay, so in the channel, the signal present is nothing but it is the FM signal which has the amplitude equal to AC, right? So the power is nothing but it is simply, okay, this is after substitution. Now the power is simply equal to what? AC square divided by 2. I have an equation like AC cos 2 pi FCT, okay, AC cos of 2 pi FCT plus 2 pi kf integral of m of t dt. So amplitude part is only just AC. Okay, so the RMS value of voltage and taking the power there with R equal to 1, we get it as AC squared by 2. That is the average power of the modulated signal. What is the average power of the noise within the message bandwidth? It is given by WN0 or N0 W. So the signal to noise ratio is given by, it is simply take the ratio of this to this. That's it. So this is the formula. So we have both the formulas now. Signal SNR at the output, SNR in the channel. Take the ratio of this to this. Okay, I'll get an equation for figure of merit. So the figure of merit is, after substituting this equation as well as this equation, I'll get it as 3 kf square p divided by w square. Fine. So in this video I have explained what is the equation for figure of merit in case of FM receivers. Fine. In my next video I will explain what is the figure of merit in case of a single tone modulation. It's a continuation of this particular topic itself. Fine. So thank you for watching this video.